Hello. Okay, so in this video, as promised, I'm going to do a more detailed and more rigorous proof of that proportionality from the main video. So in the Buffon Noodle problem, we are claiming that the expected number of crossings is proportional to the length of the noodle, no matter what the noodle shape is. And that's what we use in the proof. So here's a more detailed proof beyond sort of the hand-wavy cutting up the noodles that we did before. So there's going to be some notation. So this is the notation and the assumptions. So I'm assuming a unit grid, so square grid, where each square is length 1. And for a curve in the plane, I have gamma. So gamma is a curve in the plane. I have two notations I'm using. The length, the len of gamma, is the length of the curve. And cross of gamma is the number of times that the curve touches the grid when you throw it randomly onto the grid. This is a random variable. So its expected value is what I'm calling expected value of cross. In the video, I called that the average number of crossings. It means exactly the same thing. The reason I'm doing this notation is we'll see that having it in brackets will be like useful as we do our proofs. Like the notation actually helps understand what's going on. Okay, two more notations. So for line segments, I'm going to use the notation L for line segment, and I'm going to do a superscript with the length of the line segment. So for example, L1 is a unit line segment that you throw onto the grid. That was exactly what we did in the Buffon needle problem. That was the first thing in the video. And more generally, LX is a line segment of length X. Okay, and the thing we want to show with this notation, if I can get the mouse to cooperate, is this. So the theorem we want to show is that there is a constant C. So that was the constant we were looking for. That was the heart of the proof. A constant C, so that no matter what the curve gamma is, the expected number of crossings is C times the length of gamma. That's the thing we did. And there's a little asterisk here, so I'm technically only going to prove it for piecewise twice differentiable curves gamma. So if gamma is some super nasty curve, like maybe it doesn't touch the grid at all or something, and like something crazy can happen. But as long as you can think of gamma in pieces, and each piece is like a honest curve that has like a curvature and direction, that's all fine. So that's what we're going to do. Okay, so here comes the proof in more detail. And this proof is what I call a ladder proof. So what I mean by ladder is I think of it kind of like this, as a ladder. And the top rung, the top that we want to get to, is the theorem. And there's going to be kind of like steps on the way that are rungs of the ladder. So how many do I want? 3, 4, 5. And these are little lemmas that help get up to the proof. So there's going to be lemma 1, lemma 2, lemma 3, and lemma 4. And it's not just that there's 4 lemmas that makes it a ladder proof. The thing that, to me, makes it a ladder proof is that each of the lemmas is basically the exact same statement as the theorem, but just restricted to a smaller set. So the theorem says something for all asterisk curves, gamma. So we want to prove something is true for all curves. And the steps are going to prove it for more and more curves. So for example, step 1, lemma 1, is going to prove it for if the curve is a line segment. So let's say for all line segments. So not just any line segment, but a line segment of length 1 over n for integer n. So before we prove the thing for all, that this equation is true for all curves, we're going to first prove that it's true for curves which are exactly a line segment of length 1 over n. So these are the curves I called L superscript 1 over n. So that's lemma 1. And lemma 1 is quite a bit easier to prove than the full theorem. And once you prove lemma 1, you can get up to lemma 2. So using lemma 1, you can prove it for lemma 2. So this is the same statement as the main theorem, but instead of being true for all curves, it's for all rational length line segments. And then lemma 3 is the same thing, but for any length. So for any length of line segment. And lemma 4 is going to be true for any piecewise linear curve. Piecewise linear curve gamma. So again, we want to prove something is true for all curves, and we sort of go little by little. So first we prove it true for curves that are a straight line of length 1 over n. Then we prove it's true for curves which are rational line segments, a straight line of length m over n for some m and n. Then we prove it's true for any straight line, even if it's an irrational number. Then we prove it's true for any piecewise linear curve. This is supposed to be a gamma. And then we prove it, the final thing we want, the theorem, is the for all curves. So I call this a ladder proof because we're sort of like going up the ladder, and each step is going to help us do the next step. If you hate my messy handwriting, here I wrote them out for you here. So lemma 1, lemma 2, lemma 3, and lemma 4 are progressively increasing the set of curves for which the theorem is true. And then the theorem is going to be finally, we're going to use all of these things to prove it's true for all curves. Okay, there is also, going with the ladder analogy, there is also a ground floor. So what is the floor? The floor is, look, if this constant c is going to exist, then it has to be equal to what happens for L1. So I'm going to say that if the theorem is going to be true, the constant actually has to be, if the theorem was true, so if the theorem was true, the expected value of the number of crossings of L1, that's the straight piece of spaghetti, it's like a straight line curve of length 1, the expected number of crossings, that would be c times 1, because this is the length of the curve, so this is c. So if the theorem is going to be true, c must be equal to this expected value of the crossings of a straight piece of spaghetti. So I'm calling this the floor of my ladder proof. I'm going to take this as the definition of c. So I'm going to say define c to be this. Define c to be the expected number of crossings of the straight piece of spaghetti, a straight line segment of length 1. And then I'm going to take that as my definition of c, and then I'm going to prove lemma 1, lemma 2, lemma 3, lemma 4 using this value of c. So that's what I'm going to do. Okay, so hopefully the strategy is clear. I will say at this point, a lot of people, when they do this proof, they only prove lemma 4 implies the theorem. So like if you go on Wikipedia, they just say like, oh, it's true for line segments, and then it's true for all curves. So if you want to skip ahead to where lemma 4 is, that's totally fine. But I'm going to do the sort of more detailed proof and go step by step, because I think the steps actually like are instructive. Okay, so here we go. Lemma 1, we want to prove lemma 1. So there exists a constant c. We know what c is. C is the expected value of the number of crossings of L1. There is constant c, so that straight line segments of length 1 over n for some n have this property. The expected value is the proportional to the length. So let's prove lemma 1. So proof of lemma 1. Proof of lemma 1. Okay, so what do we want to show? Want to show the expected value of the number of crossings of L1 over n is equal to c times 1 over n. This is what we would like to show. So we're only looking at curves which are straight line segments, and they're only length 1 over n for some value of n. So these are the curves L1 over n, where n is an integer. So how do we show this? What I'm going to do is I'm going to start with the curve of length 1. So let's say this is L1. And I'm going to cut it into n pieces. So cut L1 into n pieces. Cut L1 into n pieces. So here's piece 1, piece 2, piece 3, all the way up to piece number n. And if you cut it into n pieces, you get n straight line segments, each of which are length 1 over n. So here we go. So this is, let's do this in red. So it's a length 1 over n, and this one is a length 1, this last one is also a length 1 over n. All of these pieces are length 1 over n, and there's n of them. So I'm going to count them up 1, 2, 3, 4 using subscripts. So this is L1, L2, all the way up to Ln. So I have n pieces, each of which are length 1 over n, and this is exactly the same curve as the original curve, which was one piece of length 1. Okay, how does this help us? Let's just write everything down now. So I want to start with c is equal to the expected value of the number of crossings of L1. That was the definition of c. And L1 as a curve is really the union of all these curves, L1 over n, L2 1 over n, and so on. It's the union of all these curves. In fact, it's a disjoint union. So this is actually the expected value of the number of crossings of L1, 1 over n. I'm going to write union dot for a disjoint union. Okay, I have my subscripts and superscripts backwards. L1 over n1, L1 over n2. So it's the union of these n pieces. Okay, so here's the nice thing. If you have disjoint unions, the number of crossings is the sum of the crossings of the individual pieces. So in other words, crossings are sort of linear with respect to unions. So what does this mean? So you get the crossings of L 1 over n1 plus the number of crossings of L 1 over n2 plus dot 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 plus the number of crossings of L n 1 over n. Okay, so So taking the union of all the pieces and doing the crossings, that's the same as taking the number of crossings and adding them up. Okay. The next thing is that expectation is linear. So the expected value of x plus y is equal to the expected value of x plus the expected value of y. So you can do the average before or after the sum, it doesn't matter. And I can distribute the expected value, the average, into all these pieces. So this is the number of crossings L1 over n1 plus dot 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 plus the number of crossings of L1 over n. Okay, so what have we done so far? We've shown that the expected number of crossings of the whole piece is the sum of the expected values of the crossings of the individual pieces, which is not so surprising. Okay, here is the cool thing. Because we're throwing these things randomly onto the grid, there is no difference between the expected number of crossings of one piece and any other piece. So let's compare, say, the first piece here to the last piece here. So they're both line segments of length 1 over n, and we throw them onto the grid. And sort of they don't care about the other guy. So the green little piece over here is going to be somewhere random. The red guy, I mean, it's true he's going to be near the green piece, but from his point of view, he's also just thrown randomly. So each of these pieces individually, because of the way we're throwing the full piece, each of the pieces individually are also thrown uniformly at random onto the grid. And therefore, the expected value of the number of crossings for any piece is equal. So all of these things, all of these numbers are all equal. So we're adding up the same number n times. We have L1 plus L2 all the way up to plus Ln. They're all equal. And that means, another name for adding something up n times is multiplying by n. So this is n times the expected value of the number of crossings of L1 over n. I'm going to drop the subscript. So L1 over n1 was this first piece, L1 over n2 was the second piece, and so on. But the point is all of these have the same number of expected crossings. It's the number of expected crossings of any generic piece of length 1 over n. Okay, so this is true. Okay, now we can look at where we started. C equals n times this thing. So we just rearrange the equation. C over n equals the expected number of crossings of L1 over n, which is exactly what we wanted to show. So we did it. Good for us. So maybe the proof came out harder than it actually seems. We just cut the noodle into n pieces. Each piece is identically distributed, so they have the same expected value. And therefore, the expected value of each piece is 1 over n times the expected value for the whole thing. All right, not so complicated. That's lemma 1. So we've gone one step up the ladder. Lemma 2 is almost identical. We're doing it for rational curves. So lemma 2 is almost identical. The proof of lemma 2. So we want to show that the expected number of crossings of Lm over n equals c times m over n. So if you have a straight line segment of length m over n, then its expected number of crossings is c times m over n. And we're going to do the same thing. So here's the curve Lm over n. And again, I'm going to cut it into pieces. This time I'm going to cut it into m pieces. So cut into m pieces. So I have each piece now is length 1 over n. So L1 over n1 all the way up to L1 over n m. Okay, and just like before, the expected value of the whole thing is going to be the sum of the expected values. So the expected value of cross of L m over n is equal to, so I'm going to skip some of the steps. I'm not going to write the unions out again. It's exactly the same as before. It's equal to the sum. So it's the expected crossings of L 1 over n1 plus dot 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 plus the expected crossings L 1 over n m. So each piece is length 1 over n, and there are m pieces. Okay, and just like before, all of these things are identically distributed, so they have the same mean. All of these terms are the same, so adding up the same term m times. And so that's the same as multiplying by m. So this is m times the expected value of the cross of L 1 over n. And by lemma 1, so this is where we're using the ladder, by lemma 1, the expected number of crossings of L1 over m is c times 1 over n. And that's the result. So this is equal to c times m over n. Okay, so lemma 1 and 2, we're just about cutting it into pieces and just like linearly combining them and counting them. So that's perfectly fine if things are rational. What if things are irrational? And that's what lemma 3 says. So lemma 3 is straight line segments of any length. So even irrational lengths. So this one is a bit different. This is quite a bit different than lemma 1 and 2. Let's see how this works. So lemma 3 rather. Lemma 3, we want to show. I'm gonna call the length x. Let's call it x for length. So the expected value of the number of crossings of L of x is equal to c times x. That's what we want to show. And here's what I'm going to do. I'm going to make an argument. Basically, I'm going to approximate x by rational numbers above and below. And then I'm going to make the approximation better and better, shrink the rational approximation to x. And that approximation will give me this thing. So the way I'm going to phrase this is like this. So for any rational numbers, I'm going to call them q. Q is for rational. Q minus and q plus that sandwich x. So q minus is less than x is less than q plus. So that's how I'm going to do it. I'm going to use the lemma 2, which was about rational numbers. I'm going to sandwich the number x between two rational numbers. I'm going to use lemma 2 on q minus and q plus, and I'm going to get what I want out of that. Okay, so this is really, we're using one step of the ladder to climb to the next step. Okay, so I have rational numbers q minus and q plus. How is this going to help me figure out what's going on with this stick? So this is a stick of length x, and I have q minus and q plus that are a little bit less than x and a little bit more than x. And what I'm going to do is I'm going to make an LQ minus. So we're talking about LX. I'm going to make an LQ plus. That's a line segment that's a little bit longer than x. And LQ minus, that's a line segment that's a little shorter than x. And maybe they don't have any relationship, but I'm going to create them in a very particular way. So they're not just any old line segment. They're a specific line segment. And they're the specific line segment that is a subset of LX. So I'm going to make them like this, subsets. So I'm going to define LQ minus and LQ plus. All right. Let's put the definition over here. Define LQ minus and LQ plus by, so they're going to be LX, but a little bit shorter and a little bit longer. So let's make LQ minus is this short line segment here. It lives here, LQ minus. So it's exactly on top of x, except it's a little bit shorter. It's length q minus. And by the same token, LQ plus is LX, but it's a little bit longer, which is LQ plus. And by making them on top of each other like this, as curves, they are subsets of each other. So LX is strictly, as a set, smaller than LQ plus, and LQ minus is strictly smaller than x. So we have this nice thing. And by doing it this way, when curves are subsets of each other, definitely the number of crossings they have are also going to be in order. So if, imagine crossings here. Like if there was some crossing in the Buffon Noodle problem, it can't cross, it's not possible for it to cross LQ minus without also crossing LX. And so because of that, the crossings are ordered. So the crossings of LQ minus are strictly less, or less than or equal to, the crossings of LX, which is strictly less than or equal to the crossings LQ plus. Okay, so this was the trick. By defining them to be subsets of each other, I definitely can ensure that the crossings are also in order. So this trick is called coupling in probability. So you have two random variables and you find examples of them so that they're always in order. And when they're coupled like this in order, if they're always less than each other, then the expected values are also less than each other. So therefore, the expected value of the crossings of LQ minus are less than the expected value of the crossings of LX, and that is less than or equal to the expected value of the crossing of LQ plus. So the actual, because of the way I've defined them, the actual things in order are definitely in order, and so their expected values are in order. But we've already computed the expected values of the two outside pieces in lemma 2. So this implies this one is Q minus times C. The middle piece is what we want, the number of crossings of LX. And this one is Q plus times C. Sorry about that. I was blocking the relevant piece of math. Okay, here we go. So the expected number of crossings is sandwiched between Q minus times C and Q plus times C. Maybe to add one step, let's divide it one more time. So Q minus is less than or equal to the expected number of crossings of LX divided by C is less than or equal to Q plus. Okay, so what have I shown so far? I've used this clever coupling trick. I've used lemma 2, and I've shown that you have some number x, which is the length you're looking for. You're given x, and I've shown that no matter what Q minus and Q plus are, if they're rational numbers that sandwich x, then the expected number of crossings of LX divided by C is sandwiched between Q minus and Q plus. So what number of all the numbers in the world, what number can be sandwiched between Q minus and Q plus for any Q minus and Q plus that sandwich x? The answer is it's only x. So because this is true for all Q minus and Q plus, this is going to imply that the middle guy has to be x. So this sometimes goes by some people call this the squeeze theorem. So as Q minus goes up to x, so Q minus, imagine Q minus like getting closer and closer to x, and Q plus is getting closer and closer to x from the other side, then they're going to squeeze, and they're going to force this number that we know is bounded between Q minus and Q plus, they're going to squeeze it to x. So you could say by the squeeze theorem, therefore, this expected value of the number of crossings of LX divided by C equals x. So by the squeeze theorem, maybe I'll say like since Q minus less than Q, not Q inverse, Q minus less than x is less than Q plus, I'll say are arbitrary. So because Q minus and Q plus are arbitrary rational numbers, you can squeeze them down to make x. So that's one way you could argue the proof. If you've seen soups and infs in your analysis class, what you could do is you take the soup and the inf of this equation. So take the soup over all Q minus, take the inf over all Q plus, and the soup over all Q minus is x, and the inf over all Q plus is x, and you're going to get a sandwich here with x. If you've never seen a soup and an inf, just totally ignore the last 10 seconds. Okay, so I think that we've proved it, and that we did it by squeezing. So we took our original curve and we squeezed it between two curves that we knew very well. All right, that was lemma 3. Let's scroll back up. What is lemma 4? So lemma 4, piecewise linear curves. Okay, this one is also quite easy. This one is like a lemma 1, lemma 2 type situation. Lemma 4, if gamma is piecewise linear. So let's suppose that gamma is made of n linear pieces. Gamma, let's write it as the union. Gamma is the union of a bunch of pieces. So let's call it Lx1 union Lxn. So gamma is some curve. We're saying we're only looking at piecewise linear curves. So it looks something like this. This is a picture of gamma, and it's made of n pieces, each of which are line segments of lengths x1. So this is Lx1, Lx2, Lx3, and Lx4. Okay, and we would like to show the expected value proportional thing. I'm going to just do it directly here because this one's actually really easy. So because we have a disjoint union, the number of crossings is also a disjoint is a sum. So this is the number of crossings of Lx1 plus dot 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 plus the number of crossings of Lxn. Okay, now we take expected values. Like before, like in lemma 1, expected values are linear, so it distributes. So you get the expected number of crossings of gamma is equal to the expected number of crossings of Lx1 plus all the way up to the expected number of crossings of Lxn. Okay, and we know the expected number of crossings of all of these linear pieces by the previous lemma. We're climbing the ladder. So this is c times x1 plus dot 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 plus c times xn. So each piece has a number of crossings proportional to its length, and then you factor out the c. So this is c times x1 plus dot 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 plus xn, and this is precisely c times the length of gamma. So gamma is piecewise linear. Each of the pieces are x1, x2, x3, and so on. So the sum of those is the length of gamma. So this is what we wanted to show. Okay, so let's recap what we've done so far. Lemma 1, lemma 2, and lemma 4, we're all just cutting the things into pieces. So lemma 4 we just did, we cut it into pieces. Lemma 1, we cut it into pieces, into n pieces. Lemma 2, we cut it into m pieces. So cutting the pieces and using linearity. Maybe I'll add a little note. Let's see. Lemma 1, 2, and lemma 4, these were cutting, and approximating. Maybe I'll say cutting and linear. Cutting and using linear. That's how we did lemma 1, 2, and 4. And lemma 3 had a different flavor. Lemma 3 was this coupling thing where we made one noodle fit inside another noodle, and then we knew an inequality. So lemma 3 is a really clever one. This is called, I'm going to call this coupling, and approximating. And the reason I'm bringing this up is that the proof of the main theorem, which I'm going to do next, is kind of similar to lemma 3. So it's going to use the squeeze theorem. So if you didn't understand lemma 3, you should go back and try to understand that. Lemma 3 is like a baby version of the proof we're about to do. Okay, so now I think we're ready for the main theorem. So the main theorem says that it's true for all curves. So let's do the proof of the theorem. So proof of theorem. We would like to show, want to show for any curve gamma. Okay, and any is going to mean this is piecewise twice differentiable. For any piecewise twice differentiable curve, that the expected value of the number of crossings of gamma equals c times the length of gamma. Okay, and we're going to do the same kind of squeeze theorem type argument we did before. So we're going to find two curves. Oh, I realized I told people they could skip ahead to this point. So if you skipped ahead and you skipped lemma 3, you're screwed. You got to go back and watch lemma 3. Or maybe you're just good enough you can follow without it. But so what we're going to do is we're going to find two curves, gamma in and gamma out. And gamma in and gamma out are going to be curves that approximate the curve gamma. And they're going to be set up so we can get as close to gamma as we want. So they're going to approximate gamma in and gamma out. And they're going to be, gamma in and gamma out are going to be piecewise. These are going to be piecewise linear. And because they're piecewise linear, we know their expected value using lemma 4. So lemma 4 is going to tell us gamma in and gamma out. Gamma in and gamma out are going to approximate the curve gamma. Then we're going to use the squeeze theorem just like we did in lemma 3 to get the result we want about the expected number of crossings of gamma. So that's the plan. So the only hard part is how do you construct gamma in and gamma out? What are they? And in lemma 3 we can make the curves subsets of each other. That's not going to work here because gamma is any curve. So gamma is any curve. Gamma in and gamma out, to use lemma 4, they must be piecewise linear. So we can't just say gamma in is a subset of gamma. That's not going to work. It's not going to be a subset. But what we're going to do is we're going to use convexity. So I'm calling them in and out for a reason. Gamma in is sort of going to live inside the convex shape of the convex hull of gamma. So it's going to be inside gamma, sort of. gamma is a curve, so it's not really inside gamma. And gamma out is going to be so that gamma is inside gamma out. So it's not that they're subsets, but they're going to be inside each other. They're going to be inside. So I probably sound like a crackpot. Let me show you a picture of what I mean. So suppose this is the curve gamma. Since gamma is piecewise twice differentiable, you can divide it into some number of segments where on each segment it's either concave in or concave out on that segment. Okay, or straight, but straight, don't worry about straight. Straight, we've already done. So here's my curve for gamma. Let me try a better one. So here's my example for gamma. So gamma looks something like this. And I claim all curves gamma essentially look like this. So they have some segments where they're concave in or to the left, and there's some segments where they're concave out. And there's some number of those segments. You can add up over all those segments. So here's how this is gamma in black. And here's how I'm going to construct gamma in and gamma out. So gamma in, let's do it in this red color. Gamma in. So gamma in, I said I want it to be inside gamma. So what I'm going to do, it's going to be piecewise linear. It's going to live inside gamma. So where it's concave, I'm going to go inside the concave part. So this is gamma in. So it could be something like this. Here's an example. So this is gamma in. So it lives inside the concave part. And when it's concave the other way, it's still inside. So it flips itself so that it always lives inside. So here is a version of gamma in, which has 4 line segments. You can make as many as you wanted. So again, just like before, we're saying something is true for every possible gamma in and gamma out. So gamma in here is a piecewise linear curve, and it lives inside the so some people call this the convex hull. If you don't know what convex hull is, it just means this picture. It means inside the curve, the convex hull of gamma. And if it's as long as it's piecewise twice differentiable, it's just perfectly fine. And you can make the approximation using more and more line segments, however you want. So that's gamma in. Okay, what is gamma out? Gamma out, let's do it in green over here. Gamma out. And gamma out is the same idea, but we're going to be on the outside. So it's going to be piecewise linear. And one way you can do this is you can sort of take a bunch of tangent lines to gamma and connect them up. So here's one way you can do this. So you can take a tangent line there, and then we can take another tangent line here, and we can connect them up to get a point here. So then we'll cut off the excess. So I want it to look like this. Okay, well, hold on. Okay, how about like that? There we go. So we gotta just trim them up, but you can connect up a bunch of tangent lines from gamma to get gamma out. So gamma out is, again, it's a piecewise linear, and it lives on the outside. So gamma now lives in the convex hull of gamma out. Okay, so we'll do the same thing over here. We'll take a bunch of approximations like that, and we'll connect them up to get these points. Then we'll trim off the excess. Oh no. Okay, now we really need the undo button. Huh? Okay, there you go. So there's gamma out. So gamma out is piecewise linear on the outside. Gamma in is piecewise linear on the inside. And we're going to make an argument again that works for every possible gamma in and gamma out that behave these things. So we have gamma in and gamma out. Here's the key observation. I'm going to claim that the number of crossings of gamma in is less than or equal to the number of crossings for gamma, which is less than or equal to the number of crossings for gamma out. That's the claim. Why is this true? It's true because the things we are intersecting against in the Buffon Noodle problem are straight line segments. So no matter how you draw the straight line segment of the outside grid where things are connecting, so maybe it looks like that, then it touches all of them. It could potentially touch only gamma out. So gamma out could have more. It could also touch gamma out and gamma, but not gamma in. So it looks like that. So now gamma in has strictly less crossings. But the thing that is definitely true, if the straight line touches gamma in, then it definitely touches the other two. If it touches gamma, it definitely touches gamma out. And that's exactly because of the convexity that we said. So because they live in the convex shape of each other, and because of the way they're constructed, no matter how you draw a line, the number of crossings is going to have to obey this inequality. So the number of crossings has to obey this. And I'm trying to think of if there's like a nicer way to say it or something like that, but I think maybe it's intuitively obvious. Draw some possible lines here. Any line, if it intersects gamma in, must intersect gamma. If it intersects gamma, it must intersect gamma out. That's the property we're using here. Okay, so if you believe me that this is true, this again, we've done a coupling of the curves gamma in, gamma out, and gamma so that they obey this. So this is a coupling of the curves. And now we can take the expected value. So the expected value of the number of crossings of gamma in is less than or equal to the expected number of crossings of gamma, which is less than or equal to the expected number of crossings of gamma out. Okay, so I've just taken the expected value of all the sides of this inequality. The two outside bits, because they are piecewise linear, by lemma 4, we know what they are. So this guy, this implies c times the length of gamma in is less than or equal to the expected value of the number of crossings of gamma, which is less than or equal to c times the length of gamma out. Okay. Okay, if you want, we can divide by c again. So the length of gamma in is less than or equal to the expected number of crossings of gamma divided by c, which is the length of gamma out. Okay, and this is exactly the same situation as we had in lemma 3. Now I'm going to say gamma in and gamma out, they were any curves that were on the inside and outside of gamma. So by taking a limit, by doing the squeeze theorem, we can let gamma in get closer and closer to gamma. The length of gamma in will approach the length of gamma. Similarly, the length of gamma out will approach the length of gamma from the inside, or from the other side. So the length of gamma out is going down to the length of gamma. The length of gamma in is going up to the length of gamma. And so by the squeeze theorem, or if you want soups and infs, if you're a soup and inf kind of person, you can do that as well. But by the squeeze theorem, since length of gamma in, this can converge to the length of gamma, and the length of gamma out, this can converge to the length of gamma. Therefore, the expected number of crossings of gamma divided by c is equal to the length of gamma. And then you just rearrange to get the final equation. So the expected number of crossings is equal to c times the length of gamma. That was what we wanted to show. That's the theorem. Okay, so I hope you like the theorem. I haven't seen it written down before, so it's possible I made some kind of mistake. I just made up this proof. But do double check. I think it's a really good example of these ladder proofs, which come up a lot in like measure theory and analysis, where first you prove it for some set of small functions, and you make the set bigger and bigger. So I think it's a nice proof. I really like it. Okay, I'm gonna stop there. Leave any questions in the chat, and I'll probably see it because probably almost nobody is gonna watch to this end of the video. All right, take care, guys.